Embeddings do not become good at retrieval by accident. Multiple negatives ranking loss teaches sentence transformers which matches should outrank the rest. You'll learn how the pieces fit into a workflow that trains on matching pairs and ranks the right passage above lookalikes. I'm Professor Pine, teaching AI foundations with simple Python. Search and retrieval are everywhere. You type a question and expect the right paragraph first. Off-the-shelf embeddings often look okay, but they don't always prefer the correct domain-specific match over a close but wrong alternative. That's the gap Sentence Transformers Retrieval Training fills. We teach the model which candidate should be ranked higher when several plausible options exist. At a high level, we'll turn matching text pairs into a signal that pushes the true match above everything else in the batch. The trick here is efficiency. Other positives in the batch act as implicit negatives, so you get lots of comparisons for free. The trade-off is that this only works well when your positive pairs are good and your batch sizes are sensible. Otherwise, the signal is weak. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we will try a quick baseline check with one query and one intended passage to see what the model thinks out of the box. This snippet checks one retrieval match with sentence transformers before any training. Off-the-shelf embeddings can look reasonable, but one score does not prove your domain pairs will rank correctly. The code loads sentence transformer, turns query and doc into vectors with model.encode, then asks model.similarity for the cosine style match score. That gives us a lightweight baseline before touching training data, losses, or evaluators. The printed match score shows the current model's confidence for one intended pair, which anchors the rest of the workflow. That baseline shows a single score, but we need structured training data to push the right passages above lookalikes. This example converts tiny domain matches into the shape sentence transformers expects for retrieval training. Multiple negatives ranking loss is useful when each row has an anchor and its correct positive, while the other positives in the same batch become negatives for that anchor. Dataset.fromDict keeps the input visible. Password maps to password help. Refunds map to refund help. And invoices map to invoice help. The loss object is connected to the model, so training will update that same sentence transformer. The printed training pairs confirms how many positive pairs will create the in-batch comparison signal. With pairs loaded and the loss chosen, we need to see where the current model ranks the true document among candidates. This code turns the pane into a visible ranking problem with sentence transformers. Our retrieval system does not just need a nice similarity number. It needs the right document to beat the alternatives. The query is embedded once. The candidate docs are embedded as a small corpus, and model.similarity produces one score per candidate. Max then selects the document the current model would show first. The printed top before training shows the baseline winner, so later training has something concrete to beat or preserve. Now we actually fine-tune the model on the tiny set, so the correct matches rise in rank. This snippet runs the smallest real fine-tuning step with Sentence Transformer Trainer. Multiple negatives ranking loss depends on clean in-batch comparisons. So batch samplers.noDuplicates helps avoid accidentally treating a duplicate text as a negative. Sentence Transformer Training Arguments keeps the run tiny with max steps equals 1 and uses a batch size that places all three toy pairs together. Increasing per device train batch size usually gives the loss more in-batch negatives, but it also uses more memory. The printed training loss shows the trainer completed an actual optimization step on the retrieval pairs. After training, We want an objective measure that the model ranks better across queries and a corpus. This example closes the loop with a real sentence transformer's retrieval evaluator. Manual top 1 checks are helpful, but a baseline should store queries, a corpus, and relevant docs so ranking quality can be measured consistently. Information Retrieval Evaluator embeds the query and corpus with model, ranks the corpus, and returns named retrieval metrics through results. Setting write CSV equals false keeps the tutorial focused on the in-memory score instead of files. The printed retrieval nDCG reports the evaluator's primary ranking metric, giving the mini project a repeatable success signal. Applied to a real support corpus, this tiny loop maps directly. Build a dataset from your FAQ question and answer pairs. Run the same training step with a larger batch and more steps. Then evaluate on a held-out set of queries and relevant documents to measure real gains. In short, this trains embeddings to prefer the true match over lookalikes. Use it when you have labeled pairs and need better ranking than generic embeddings offer. One caveat is that batch composition and pair quality strongly affect learning. A practical next step is to index the trained embeddings with FAISS and tune nList and nProd to trade off latency and ranking accuracy on your dataset. That will show how training gains translate to real query speed and top K quality. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.